Students, how are you? Today we'll start Zitli chapter number 3, article number 3.6.2. The article name is tertiary states or the time independent potentials. In general, we know that the Schrodinger equation of a body of mass m is moving in a potential field have the value iota h cut curly by curly t psi of rt is equal to minus h cut square over 2m del square v psi of rt plus v of rt psi of rt. From this equation we know that this equation depend on the value on two things. One is the value of r, the other one is the value of time. So this is not a time independent potential here, but for a special case we said that the potential in this equation depends only on the value of r instead of time t, so they are time independent potentials. So we can say v of rt is equal to v of r, not t, because it is independent of time. So as the potential is independent of time, so the Hamiltonian which is involved in this equation will also depend on the value of r instead of time t. So the Hamiltonian is also a time independent as the potential is also time independent. And the solution of this Schrodinger equation, which is time independent, will be a product of two functions, one which will depend on the value of r and the other one which will depend on the value of time. Why? Because one side of the equation, the right hand side, involves two things. One is the potential, the other one is the Hamiltonian, and both of these things, both of these terms are independent of time, while the left hand side of the equation here is curly by curly t, which is the time derivative. So we can say that the right hand side of the equation depend on time, left hand side, sorry. So left hand side depend on time, the right hand side is independent of time. So in this way we can say that our solution will be in such a way that it will be a product of two things. One state is must be independent of time, the other state will be dependent of time. So we will define a solution from ourselves that psi of rt, this is our imaginary solution, psi of r and f of t, this is our imaginary solution. We suppose it that this is our solution, so we will substitute this value psi of rt in our general equation of Schrodinger equation in general form. Iota h cut curly by curly t, here is psi of rt. So instead of psi of rt we will substitute psi of r f of t, psi of r and f of t is equal to the right side. Right side is minus h cut square over 2m into del square here psi of rt, and we will place the value of psi of rt as psi of r and f of t plus v of rt. Here's v of rt. We will not write here v of rt because the potential is time independent, so only v of r, and psi of rt, instead of psi of rt we will substitute psi of r and f of t. Here on the left hand side of the equation, here is time derivative, so we will use f of t as a variable and psi of r as a constant. So we will write iota h cut psi of r, because it is constant, curly by curly t, and f of t as a variable. As here we use only one derivative, only one variable, which is time, so we will use ordinary derivative instead of partial derivative. We can say d by dt instead of partial derivative, minus h cut square over 2m del square. Here we know that potential and Hamiltonian are independent of time, so f of t in both of these terms will be constant. We will make it separate, psi of r into f of t, and dividing both sides of the equation by psi of r f of t, we will get h cut square as iota h cut psi of r d by dt f of t divided by psi of r f of t minus h cut square over 2m del square psi of r plus v of r psi of r f of t divided by f of t psi of r. F of t cancel out and here psi of r cancel out. So iota h cut d by dt f of t is equal to minus h cut square over 2m del square psi of r plus v of r psi of r. Here we remember that we know that the value of del is equal to curly by curly t plus curly by curly y, curly by curly x plus curly by curly y plus curly by curly z. The value of del does not depend on time, so that's why we said that Hamiltonian is also independent of time. So from here we can say that left side of the equation is iota h cut d by dt f of t. This is energy. We can say that it is energy E. D by dt f of t. When we take this, the value of this iota h cut to the other side, we can write it as we can say. But here at this time, sorry for this. Here f of t, we cancel out psi of r with psi of r, and here we have f of t. Here also we have f of t. When we take this f of t to the other side, it will become E f of t. And the right side of the equation is h cut square over 2m del square psi of r plus v of r psi of r 1 over, we remember that here psi of r will be as it is because this is not cancelled out with anything else. So 1 over psi of r is as it is. Here psi of r as it is, and this is also equal to energy minus h cut square over 2m del square psi of r plus v of r again plus into psi of r equal to E, and this psi of r, when we take it to the other side, it will multiply with this energy is equal to psi of r. The solution of this equation, of the Schrodinger equation, will become f of t is equal to e power minus iota e t over h cut, and the value of the state function psi will be equal to u of rt is equal to psi of r and f of t. So the value of f of t is e power minus iota e t over h cut, and we remember both of these things. We say that the state or the system is still time independent. Why we said it? Because the probability density of this function is independent of time. We can write it here or in another place, like here. Psi of rt mod square is equal to psi of r and e power minus iota et over h cut mod square is equal to psi of r mod square. So here we can say that the probability density of the function is independent of time. And also be remember that the solution of this equation will give us the states which are bound and unbound states, and these bound states and unbound state give us the spectrum of the function and of the function of the system, and the bound states are called the discrete spectrum and the unbound states are called the continuous spectrum of the system. Hope so you can understand all of this.